Conrad and Bean received more mission-specific training than Apollo 11's Neil Armstrong and Buzz Aldrin had. This was in addition to the 1,500 hours of training they received as backup crew members for Apollo 9. The Apollo 12 training included over 400 hours per crew member in simulators of the command module and of the LM. Some of the simulations were linked in real time to flight controllers in mission control. To practice landing on the Moon, Conrad flew the Lunar Landing Training Vehicle, training in which continued to be authorized even though Armstrong had been forced to bail out of a similar vehicle in 1968, just before it crashed. Had Apollo 11 not succeeded, Apollo 12 would have flown in September 1969, but with the successful landing on the Moon, Apollo 12 was moved back to November and later Apollo missions were also put on a more relaxed schedule. Soon after being assigned as Apollo 12 crew commander, Conrad met with NASA geologists and told them that the training for lunar surface activities would be conducted much as Apollo 11's, but there was to be no publicity or involvement by the media. Conrad felt he had been abused by the press during Gemini, and the sole Apollo 11 geology field trip had turned into a near fiasco, with a large media contingent present, some getting in the way. The astronauts had trouble hearing each other due to a hovering press helicopter. After the successful return of Apollo 11 in July 1969, more time was allotted for geology, but the astronauts' focus was in getting time in the simulators without being preempted by the Apollo 11 crew. On the 6 Apollo 12 geology field trips, the astronauts would practice as if on the Moon, collecting samples and documenting them with photographs, while communicating with a Capcom and geologists who were out of sight in a nearby tent. The astronauts' performance in choosing samples and taking photographs would be critiqued. To the frustration of the astronauts, the scientists kept changing the photo documentation procedures. After the 4th or 5th such change, Conrad required that there be no more. After the return of Apollo 11, the Apollo 12 crew was able to view the lunar samples and be briefed on them by scientists. As Apollo 11 was targeted for an ellipse-shaped landing zone, rather than at a specific point, there was no planning for geology traverses, the designated tasks to be done at sites of the crew's choosing. For Apollo 12, before the mission, some of NASA's geology team met with the crew and Conrad suggested they lay out possible routes for him and Bean. The result was 4 traverses, based on 4 potential landing points for the LM. This was the start of geology traverse planning that on later missions became a considerable effort involving several organizations. The stages of the lunar module, LM-6, were delivered to Kennedy Space Center on March 24, 1969, and were mated to each other on April 28. Command Module CM-108 and Service Module SM-108 were delivered to KSC on March 28, and were mated to each other on April 21. Following installation of gear and testing, the launch vehicle, with the spacecraft atop it, was rolled out to Launch Complex 39A on September 8, 1969. The training schedule was complete, as planned, by November 1, 1969. Activities after that date were intended as refreshers. The crew members felt that the training, for the most part, was adequate preparation for the Moon mission. There were no significant changes to the Saturn V launch vehicle used on Apollo 12, SAW 507, from that used on Apollo 11. There were another 17 instrumentation measurements in the Apollo 12 launch vehicle, bringing the number to 1,365. Of this figure, the spacecraft weighed 110,044 pounds, up from 109,646 pounds on Apollo 11. The third stage of the Saturn V, the SIVB, was intended to fly into solar orbit. The SIVB auxiliary propulsion system was fired, with the intent that the Moon's gravity slingshot the stage into solar orbit. Due to an error, the SIVB flew past the Moon at too high an altitude to achieve Earth escape velocity. It remained in a semi-stable Earth orbit until it finally escaped Earth orbit in 1971, but briefly returned to Earth orbit 31 years later. It was discovered by amateur astronomer Bill Young, who gave it the temporary designation J002E3 before it was determined to be an artificial object. Again in solar orbit as of 2021, it may again be captured by Earth's gravity, but not at least until the 2040s. The SIVBs used on later lunar missions were deliberately crashed into the Moon to create seismic events that would register on the seismometers left on the Moon and provide data about the Moon's structure. The LES contained 3 rocket motors to propel the CM to safety in the event of an abort shortly after launch, while the SLA housed the LM and provided a structural connection between the Saturn V and the LM. The SLA was identical to Apollo 11's, while the LES differed only in the installation of a more reliable motor igniter. These sea-related names were selected by the all-Navy crew from several thousand proposed names submitted by employees of the prime contractors of the respective modules. George Glacken, a flight test engineer at North American Aviation, builder of the CSM, proposed Yankee Clipper as such ships had majestically sailed the high seas with pride and prestige for a new America. Intrepid was from a suggestion by Robert Lambert, a planner at Grumman, builder of the LM, as evocative of this nation's resolute determination for continued exploration of space, stressing our astronauts' fortitude and endurance of hardship. The differences between the CSM and LM of Apollo 11, and those of Apollo 12, were few and minor. The hydrogen separator was added to the CSM to stop the gas from entering the potable water tank. Apollo 11 had one, though mounted on the water dispenser in the CM's cabin. Gaseous hydrogen in the water had given the Apollo 11 crew severe flatulence. Other changes included the strengthening of the recovery loop attached following splashdown, meaning that the swimmers recovering the CM would not have to attach an auxiliary loop. LM changes included a structural modification so that scientific experiment packages could be carried for deployment on the lunar surface. 2 hammocks were added for greater comfort of the astronauts while resting on the moon, and a color television camera substituted for the black and white one used on the lunar surface during Apollo 11. The Apollo Lunar Surface Experiments Package, or ALSEP, was a suite of scientific instruments designed to be emplaced on the lunar surface by the Apollo astronauts, and thereafter operate autonomously, sending data to Earth. Development of the ALSEP was part of NASA's response to some scientists who opposed the crewed lunar landing program by demonstrating that some tasks, such as deployment of the ALSEP, required humans. In 1966, a contract to design and build the ALSEPs was awarded to the Bendix Corporation due to the limited time the Apollo 11 crew would have on the lunar surface. A smaller suite of experiments was flown, known as the Early Apollo Surface Experiment Package. Apollo 12 was the first mission to carry an ALSEP. One would be flown on each of the subsequent lunar landing missions, though the components that were included would vary. Apollo 12's ALSEP was to be deployed at least 300 feet away from the LM to protect the instruments from the debris that would be generated when the ascent stage of the LM took off to return the astronauts to lunar orbit. Apollo 12's ALSEP included a lunar surface magnetometer, to measure the magnetic field at the moon's surface, a lunar atmosphere detector, intended to measure the density and temperature of the thin lunar atmosphere and how it varies, a lunar ionosphere detector, intended to study the charged particles in the lunar atmosphere, and the solar wind spectrometer, to measure the strength and direction of the solar wind at the moon's surface. The freestanding solar wind composition experiment, to measure what makes up the solar wind, would be deployed and then brought back to Earth by the astronauts. A dust detector was used to measure the accumulation of lunar dust on the equipment. Apollo 12's passive seismic experiment, a seismometer, would measure moonquakes and other movements in the moon's crust, and would be calibrated by the nearby planned impact of the ascent stage of Apollo 12's LM, an object of known mass and velocity hitting the moon at a known location, and projected to be equivalent to the explosive force of 1 ton of TNT. The ALSEP experiments left on the moon by Apollo 12 were connected to a central station, which contained a transmitter, receiver, timer, data processor, and equipment for power distribution and control of the experiments. The equipment was powered by SNAP-27, a radioisotope thermoelectric generator developed by the Atomic Energy Commission. Containing plutonium, the RTG flown on Apollo 12 was the first use of atomic energy on a crewed NASA spacecraft. Some NASA and military satellites had previously used similar systems. The plutonium core was brought from Earth in a cask attached to an LM landing leg, a container designed to survive re-entry in the event of an aborted mission, something NASA considered unlikely. The cask would survive re-entry on Apollo 13, sinking in the Tonga Trench of the Pacific Ocean, apparently without radioactive leakage. The LAD returned only a small amount of useful data due to the failure of its power supply soon after activation. The LSM was deactivated on June 14, 1974, as was the other LSM deployed on the Moon, from Apollo 15. All powered ALSEP experiments that remained active were deactivated on September 30, 1977, principally because of budgetary constraints. With President Richard Nixon in attendance, the first time a current U.S. president had witnessed a crewed space launch, as well as Vice President Spiro Agnew, Apollo 12 launched as planned at 11 hours 22 minutes and 0 seconds on November 14, 1969 from Kennedy Space Center. This was at the start of a launch window of 3 hours and 4 minutes to reach the Moon with optimal lighting conditions at the planned landing point. There were completely overcast rainy skies, and the vehicle encountered winds of 151.7 knots during ascent, the strongest of any Apollo mission. There was a NASA rule against launching into a cumulonimbus cloud. This had been waived, and it was later determined that the launch vehicle never entered such a cloud. Had the mission been postponed, it could have been launched on November 16 with landing at a backup site where there would be no surveyor, but since time pressure to achieve a lunar landing had been removed by Apollo 11's success, NASA might have waited until December for the next opportunity to go to the surveyor crater. Lightning struck the Saturn V 36.5 seconds after liftoff, triggered by the vehicle itself.